Okay, continuing with our discussion of higher order derivatives, we're going to see that in definition 2.9 that the derivative of the position function of a flying object or any moving object is going to be the velocity function, and so that's the velocity of the object. And then the derivative of the velocity is actually going to be the acceleration, so that's the rate of change of the velocity. So an example here, in example 220, is that a ball is thrown upward from the top of an 80-foot parking garage. The initial velocity is 50 feet per second, which implies that the position function of the ball is negative 16t squared plus 50t plus 4. It says find the height, velocity, and acceleration of the ball at t equals 2 seconds after the ball is thrown. So to get the height, all you do is plug in p of 2, that's the position at 2, or height at 2. So you'll get negative 16 2 squared plus 50 times 2 plus 40. And I don't have a calculator handy, but you can do that math. And then next you're asked to find the velocity. Well, the velocity is the derivative of position with respect to time. So there you'll get negative 32t plus 50. Okay, and that 50 there is the initial velocity of 50 feet per second that we saw. And so now this is saying that our velocity at time 2 is going to be negative 32 times 2 plus 50 is negative 64 plus 50, so it's negative 14 feet per second. Okay, so after 2 seconds, that's saying that the ball is actually falling at a rate of 14 feet per second. And finally, the acceleration is going to be the second derivative of the position. So that's ddt of the position, or that's the derivative of your velocity. So it'd be like dv dt. And so that's just going to be negative 32 feet per second squared. Okay, and this is actually accurate, that the force due to gravity is always negative 32 feet per second squared on the surface of the Earth. Okay, and so there's your height, your velocity, and your acceleration at time 2.